Hello. In this lesson, we're going to talk about accuracy as compared to precision, and then we'll learn a little bit about calculations involving measured quantities, where we need to pay attention to the number of significant digits that are involved. You've got your guided student notes ready? Let's get started by looking at the difference between accuracy and precision. In casual language, people tend to use accuracy and precision interchangeably, but the truth of the matter is that they have different meanings, and it's important for us to know what the words mean, because when we communicate with people, we want others to see us as educated professionals in our field. So we make sure that we use precise language and good vocabulary. Let's get started here. Accuracy describes how close a measured value is to the true value. If you measure something and claim that it is 2 inches long, that's what you say. But 2 inches is not going to be the exact length of something. The actual exact length, down to as many decimal places that you may want, is completely different from 2 inches that you said. So that's accuracy. It says how far away is what you said from what the actual result actually is. All right, anyway. Precision is different. Accuracy talks about how close a single value is to the truth. Precision talks about a set of values. Precision is concerned about whether or not results are repeatable. So precision describes how close repeated measurements are to each other. All right, so it's probably better if we have some pictures. So here we have some bullseyes, and the little blue dots represent the measurements, and the very center of the bullseye is the truth. So when we look over here on the left, we have a really nice grouping, but it's nowhere close to the center. This nice grouping means that we are precise. Hang on, let's fix that. Okay, I think I've got it fixed. At any rate, we have this nice little grouping over here, and this means that things are precise because all of the results are close together, but they're nowhere close to the center. So these are not accurate. My mother used to do this thing with a scale where she would set it to be 5 pounds heavier than it actually was. So this is sort of that idea. The scale would give consistent readings, but they would be far away from the truth because that's the way that she had set it. Over here on the upper right-hand side, we have a lot of values that are really close to the center, but they're pretty spread out. Being close to the truth, being close to that center, makes us accurate. But being spread out means we are not precise. On the lower left, we've got a mess. These are not all close to the center, and they're also not together. This is what might happen if we were on a road trip and somebody said, hey, how many hours is it going to take us to get there? And I just took a die and rolled it, and whatever the number was would be the number of hours I would say. So if the road trip was actually going to take 2 hours, this little dot here would have been close to the truth by accident. And all of these are just crazy. So it's not anything that's repeatable. This is not precise and is also not accurate. The reason why people use precision and accuracy interchangeable is because we want both. We expect both. We have a lot of situations in which we get both. A nice cluster here in the middle, everything is close together, and everything is close to the truth. So this is the picture that is precise and accurate. All right, so there's the difference between accuracy and precision. A while ago, we talked about tolerance. And tolerance actually describes an amount of inaccuracy that's allowed. Remember, accuracy talks about how far you are away from the truth. So when we say we have a tolerance, that says how far away from the truth can you be, and it's still all right. And then finally, before we flip the page, we want to talk about exact values. With exact values, there is no uncertainty associated with the value. There is no uncertainty. When you open up a brand new carton of eggs, you expect to see 12 eggs, and 12 eggs there are. That's it. Nobody's going to count them any differently. There is no uncertainty associated with the value. 12 eggs make a dozen. And not only that, but you haven't rounded a thing. You could report that 12 is 12.00000 with infinitely many zeros, and it would still be exactly correct and perfect. No part of the value has been rounded. We never say that there are about 12 eggs in a dozen. There are 12 eggs in a dozen. So no part of the value has been rounded. All right, let's flip the page and see what's coming up next. Ah, look at that, just a little bit more vocabulary. So we had exact values. Measured values are different. So things that you count are exact. Things that you measure with some sort of device will always involve approximation. We have a lot of digital measuring devices in our world now, but they are still things that are approximating. They can only tell you down to a few decimal places how big something is. They can't give you infinitely many decimal places like an exact value can. So measured values involve approximation. They all have a limited number of reliable digits. They have a limited number of reliable digits. When we talk about the precision of a measuring instrument, this means what is this tiniest amount, the smallest change that the instrument can detect. It is the smallest notice, oh my goodness, my tongue has stopped working. The smallest noticeable increment. So every measuring instrument, no matter how precise it is, has some error associated with its results. We define this as the greatest possible error of a measurement, and it's pretty easy to calculate. It's just half the precision of the measurement. So let's see what we mean here. Let's go to the track. Judith has a stopwatch. Emil is running. Emil runs the 100-meter dash in 12.3 seconds, according to Judith's stopwatch. We know that that is not exactly the truth out to an infinite number of decimal places. There's some rounding error in there. There's also probably a little bit of operating error in there for when you clicked and unclicked the stopwatch. But at any rate, we'll just ignore the operating error for just now. What is this stopwatch doing? Well, right here is the far right digit in the tenths place. So the precision of this instrument is the nearest tenth of a second. That's the smallest difference that the stopwatch can register. What was Emil's actual time? Well, we don't know. What we do know is the bounds on it. When the stopwatch registers 12.3 seconds, what it's actually saying is that the truth is stuck between, or is one of the possibilities of things that actually rounds to 12.3 seconds. So Emil's actual time could have been as low as 12.25 seconds. That would have rounded to 12.3. It also could have been as high as 12.35. We'll keep a strict inequality here because you know the 5 is going to push that 3 up to a 4, but we'll put an equals down here because the 5 does round things up to the 3. And there you have it. The truth is somewhere between 12.25 seconds and 12.35 seconds. The greatest possible error is 1/2 of the precision, which is 0.05. And that, of course, is the difference between this edge and the middle that was reported. Okay, that's pretty much it. Precision, the actual, and the greatest possible error are all related, and figuring them out is pretty straightforward. Pause the recording and you try example 2 on your own. Come back when you're ready. All right, so Frances is watching this race as well, and she has a more precise stopwatch. Hers is precise to the 1/100th of a second. And this means that she has figured out the actual time is somewhere, something that rounds to 12.27. 12.275, if we were just a little bit below that, would round to 12.27, and 12.265 would round up to 12.27. Now you can see that this interval here is much tighter than it was before, and that's what being more precise is all about. The greatest possible error is 1/2 of the 1/100th of a second, .005, the distance between the reported value and the farthest value that would round to that number. If we're working on a ruler, a US ruler that was measuring in inches, we would have different types of subdivisions. They would be fractions or fractional. So this ruler has subdivisions of 1/16 of an inch. We use the smallest subdivision possible. That's our precision. The greatest possible error is still 1/2 of that. And hopefully you remember how to measure, how to multiply fractions, and you know that that's worth 1/32 of an inch. All right, so let's flip the page and talk a little bit about significant digits. We use significant digits to communicate with other people about the precision of the measurement. So significant digits convey information. about the precision of a measurement. So the first thing we do is look at a measurement and decide which digits are significant and which digits are not. And the rules for the most part are pretty easy. If it's not a 0, it's definitely significant. We wrote that number down on purpose. Zeros are where we have to be careful. Any 0 that's used as a placeholder is not significant. It's just something you had to put in so that the other digits were in the right spots. If you intentionally put a 0 down, other than as a placeholder, then that 0 is significant. So the idea is that in number A here, this 0 is in the middle and this 0 is in the middle. Both of these are significant because they're not at the beginning or the end of a number. This value would have 1, 2, 3, 4, 5 significant digits. The second one here only has 2, right there. The other zeros are just placeholders. And the one down here, well, what do you think? Yes, that has 5. The 0 in the middle doesn't matter. So 1, 2, 3, 4, 5. Also 5 significant digits. The problem comes when we're working with whole numbers, large whole numbers that end in zeros. It's sometimes kind of hard to tell which of the zeros are significant and which of the zeros are not. One thing that we can do is rely upon our knowledge of the situation. You can imagine if a 0 was replaced by a 1, is it a measurement that you would possibly obtain in the same situation? For example, if you went down and you looked at the reading on your water meter and you saw 81,000 cubic feet of water had been used, would it be sensible for you to look at the water meter in a little while and see 81,001 cubic feet? Could you do this? And would you see a reading like that? And the answer is yes, you would. Since you would see a reading like that, well, just imagining that one, it's not really there, then all of these zeros are significant. So this one has 5 significant digits because 81,001 would also be displayed. Your water meter can read down to the nearest whole cubic foot. It doesn't count by thousands at your house. If we were talking about the population of a city, however, that's a whole other story. We don't generally tend to know down to the single person how many people are in a city. Even if we were doing a census, we wouldn't know this thing. This is a rounded value. It's been estimated. It's approximated. Approximated to where? Well, we could talk about that. Not to the nearest whole number, probably not down to even the nearest 10. So it's possible this is to the nearest 1,000 or to the nearest 100. So we would say maybe 2 or 3 significant digits. That rounding to the nearest 100 or the nearest 1,000 is sensible. Well, we have to pick one. Do we want 2 significant digits or do we want 3 significant digits? And since we really don't know what happened in this city, we're not sure. So if we're ever in doubt, we are not going to count the zeros on the end of a whole number. So this says do not count the zeros on the end of the whole number, which means that 81,000 would have 2 significant digits. Now, in technical fields, we have to be able to tell people how many significant digits we have. We can't just go around deciding that the zeros count or the zeros don't count depending upon how we're feeling that day. So what do people do? And there are a couple of options. One thing that happens, hang on, there, that's better. One thing that happens is that people underline a zero if it's significant, or at least the far right zero of all the significant digits. So let's look at this idea of 81,000 again. And let's imagine a couple of different scenarios. Here, 81,000 with the 0 in the hundreds place underlined would contain 3 significant digits, all of those. And that would tell us that this number was rounded to the nearest hundred. Another option is to actually write down how many significant digits you have. So maybe we want to tell people that this 81,000 actually contains 2 significant figures. This F is for figures. They don't tend to call them SDs. They use SF for significant figures. At any rate, that would tell you that only these count. It doesn't matter what digits they are, those are the ones that count. It specifically says we have 2 significant digits. And in this case, the 81,000 was rounded to the nearest 1,000. If we went back up to this one again and thought that this 0 was underlined, then we would have 4 significant digits, and the value would have been rounded to the nearest 10. The last thing we can do in a technical field is to use scientific notation. Well, yeah, it's science, it's technology, it's a technical field. They go together. If you want this 0 here to be highlighted as important, then scientific notation allows us to do that. We write down everything that matters in scientific notation. This one would have 3 significant digits because every digit in the coefficient of a number, so the coefficient is this part. If you write the digits down in the coefficient, they matter. Well, it's that easy. We don't have to worry about what matters and what doesn't. Okay, so how do we do arithmetic with measured quantities? You'd think we'd do it the same way that we have been doing it, but the truth of the matter is we've been doing it without paying attention to the details until now. When you have a measured quantity, there's always some error, and adding or subtracting to it sometimes makes a difference and sometimes doesn't. So imagine, for example, that we're talking about Donald Trump. At one time, somebody reported his net worth as being $3.9 billion. Donald Trump could walk down the street and drop a quarter, and he would never notice. You and I might notice. Might be my last quarter. Donald Trump could go to a restaurant and leave a waitress $1 million tip. $1 million tip! And it wouldn't change how people reported his net worth. $1 million is so small compared to 3.9 billion that leaving that sort of tip at a restaurant wouldn't change a